Yeah, then they can start joining in.
Yeah. We'll give it a few minutes. I just started it now, so we'll give it like 5 minutes for people to come in, pop in.
All right.
I'll start it.
Okay. Turn my phone off. Yeah, we got a little snow out here.
Yeah, we're gonna get hit big this weekend.
I know, right in time for me to go to Las Vegas. So.
Oh, when are you leaving?
I'm leaving Saturday, and it's like a super early flight, so I hope I can get to the airport. So.
Oh, you might be in trouble.
I know. I was like, oh no. So. Yeah, and it looks like it's going to be a doozy. So. Yeah.
Yeah, last time I was at the Vegas ASHRAE was probably, I guess, 10 years ago.
Yeah.
And we were out there, and there was a storm in New York, and I got stuck in Vegas for a whole week.
Oh my God! Yeah.
Couldn't get flights back. Any flight back was all booked. I was trying to get flights into Philly to drive. That was all booked.
Yeah, I remember that. Yeah. People have. You remember the show in New York when you had? Oh, that was horrible. Everybody was stranded, and the buses were backed up. Everybody was walking through all that snow. Oh, it was terrible.
Yep, I remember that too.
Oh, it's terrible. I think they should have it in Chicago every year. It's always the best, man. I love going to Chicago for ASHRAE. It's just like people are focused. There's not a lot to do, so they come to the show.
Vegas is a little tough.
Vegas is tough. There's not going to be nobody there, man.
You might get some people Monday morning. Tuesday, Wednesday is going to be dead.
I know. It's going to be totally dead.
All right, I'm going to get started.
All right, cool.
After 12.
Sure.
Welcome, everybody. Happy New Year to you all. This is our first class of the year. We kind of took a break between the holidays, knowing people would be away and it'd be tough to get people on board. So just keep an eye out on the website. Every couple of weeks we'll have a class. That's our goal. Most of them will have PDH credits, some will not. We'll post which ones do and which ones don't. Today I have Danco helping us out with an introduction to chill beam and radiant HVAC. Again, those of you, if you can just shoot us an email at academy@gilbar.com just to say, let us know that you require a PDH certificate, so I can put you on the list and make sure you get it. Any other questions that need to be asked through the presentation, use our chat feature. And I don't think there's that many people on board, so as they come up on the chat feature, I'll read them out to Giancarlo, and we'll try to get them answered for you. And we'll do a quick Q&A at the end as well. We'll give a few minutes of that. And other than that, I'll let Giancarlo take over, and we'll go from there. Thank you.
All right, thanks a lot. I'm Gianca. I've been with Mestek for 28 years. I'm the regional sales manager for Danco. And I really appreciate you guys at Gil-Bar doing this. We have a really good connection with you guys in New York and done a lot of jobs together. And I hope that you guys find this content interesting. And if you want more information, please contact Gil-Bar or myself, and we can get that to you. I can do personal training. We can do sizing, selection, and if you go to our website, Danco.com. It has all the information that you need there. And again, please contact the guys at Gil-Bar if you have any other information. Danco is a part of Mestek, so it's like Mestek's like the holding company, and these are a bunch. I just put a bunch of the products that we have underneath Mestek, which I've worked for a lot of these different companies over the years. But currently with Didenko, and Didenko makes active chill beams and radiant products, and that's what we're going to be discussing today, and just kind of go over the basics of it. This is my facility up here in Westfield, Massachusetts, and we invite all of you to come visit. It's a training center. It's a LEED Gold facility, so that means that it's energy efficient. We wanted to make this facility to show you that we know what we're doing. We walk the walk. We've designed a lot of net zero buildings and things like that with Radiant, with other products. So this training facility, we made it for you guys to come. Unfortunately, with the current climate, it's hard to meet face to face. That's why we're doing more of these internet-based things, and we really appreciate you guys coming and joining us here and learning about our products and learning about the things that we have to offer you guys. But this facility is open for you guys to come tour, and we have presentations in all these different demo spaces. So we do a lot of work with active chill beams and radiant in labs. So we have a full working laboratory. This laboratory has different arrays of active chill beams with working air hoods. And I know that Gil-Bar also has a demo out in Long Island, which I've been to a number of times. And we can arrange presentations to show you how our products interact with the various other products to make a very energy efficient, clean, safe, and comfortable lab facility. So we have those demo rooms here in Massachusetts as well, out on Long Island. So we invite you guys to come. We love guests, and we know that currently it's a little difficult, so that's why we're doing it online, but hopefully we can start meeting face to face soon. Makes a big difference when you can touch, feel, and see how actually these products work. So that's why we develop these things. We also do a lot of work in hospitals. So we have a hospital demo room. Hospitals work really well. We've done a lot of stuff in NYU and working on a current job there with Gil-Bar on that, designing with the engineer and things like that. But using a patient room, basically by code. I'm going to turn off my heater because I think it's making a little noise. Hold on a second. In a hospital room, you need 4 air changes by code. So basically, if you're using 55-degree air with 4 air changes in a hospital, you're overcooling a lot of times. So reheat is a big deal in hospitals. So there's a lot of energy to be saved using active chill beams. I'm going to talk about the principles of active chill beams. I have a whole presentation on hospitals, and if you're interested, please let me know. I can go through that with you guys as well. But basically, it'll save you a lot of energy by eliminating reheat, as well as if you're using a dedicated outdoor air system in conjunction with an active chill beam. Basically, it's a lot healthier because you're not mixing the air from this room across the whole hospital. So you're using 100% outdoor air with an active chill beam, eliminating reheat, and it's a lot healthier, safer, and energy efficient. So we show you how to do that. This is our hotel room. We do a lot of induction replacement, especially in New York. That's what showed here down along by the bed here. This is an induction unit. And we have a hot and cold wall which you can simulate heating and cooling with this wall. And then show with induction units how we could take those induction units, put them in the ceiling in this grill. And then we have another one which is a horizontal unit, show different throws and the comfort of using these products in a hotel or an office environment. We also do a lot of work in classrooms. Classrooms are a big one for us. A lot of times it's due to the sound requirement. You need to be below 35 NC in a classroom. Active chill beams are by nature super quiet. Also, you get very, very good air exchange in there. So we use a lot of times, we show them how to use them in a classroom environment. Conference rooms, office space. You can mix radiant panels with active chill beams, and we show you how to do that with this in a cloud system in this environment. Of course, office space is kind of where we use active chill beams and radiant a ton. So we show how to do that. And then we show you how to all tie it all together. So of course, Mestek makes a bunch of different products, including boilers. So we have these stage condensing cast iron boilers. This boiler room has different color-coded water temperatures. So the red is the high heat, the orange is the medium heat. The medium heat we have connected to a dedicated boiler. That boiler is condensing. It's a lower temperature. And that way, by using that lower temperature, we're always in that condensing mode. So we have a dedicated boiler, which makes it a lot more efficient. And then we have green and blue. Blue is our low temperature water. That's connected to our DOAS unit way in the back. And then that's mixed to get our medium chilled water, which is a 56-degree water, which serves our active chilled beams. So we show how to tie all of that together and all the different products that you can use to make an energy efficient system. So it's really not just the end product, it's about the entire system, and we show you how to set all those things up, including the control system. So how to set up those controls, how to have different modes for return air, dedicated outdoor air, energy recovery wheels, and those kind of things. So, and then the other thing that's kind of the biggest deal here that we have at this is we have a lab. This energy lab has a hot and cold wall. So these are radiant panels that are on the wall, which represents heating and cooling through the skin of the building. And then we have these DIN men. The DIN men basically represent a person and a computer. And we can basically mock up any room that you guys have or facility and show you exactly how our products are going to interact with that space. Make sure it's meeting the loads for heating and cooling. We can show the different throws. We can show when it's going to condense. If you're worried about condensation, the temperature is at different levels. So we can fully set up any kind of scenario that you guys that basically fits into this room. We can kind of model it with this room. So we invite you guys to take advantage of that as well. All right, so why are these things green, and where are they used? And basically, in buildings today, they're huge energy hogs, and we're looking more and more to make it more energy efficient. So what are the primary factors driving energy consumption in buildings? The first is your building envelope. And we tell everybody, if you're going to spend your money, spend it on your windows. And I know in New York, there's a big issue with, a lot of the older buildings with the facades aren't great. And really, the best way to drive down your energy consumption is to work on your building envelope, make it tight, put in better windows. That's what we did at our Lux and Reed Center, and we were able to get that LEED Gold standard by basically putting in better windows and good insulation in the building. The other thing is lighting. Lighting's coming obviously a lot better these days than back in the day, but we're going to be focusing on our HVAC systems. Basically, what we're going to be targeting is fans. So when you talk about energy consumption, a lot of the problem with buildings is moving that energy around the building. And typically that's used with fans. The problem with fans is they're not as efficient as water. So we're talking about hydronics here, water, and basically the efficiency between water and air is 10-to-1. And this is an important concept for you guys to understand, because this is the magic that's behind all this. This is what makes it green. There's a lot of operating procedures and things like that which will also get you energy efficiency. But the primary reason why active chill beams and induction units and radiant panels are efficient is because of this principle. So for 1 ton of cooling, it requires 550 CFM of air or 4 GPM of water in a 3/4 inch water pipe. So you can physically see, and that's because water holds energy better than air does. And the other thing with air is it's leaky, it makes a lot of noise, and it's compressible. So if you think about those buildings in New York City, you have this huge column of air going up 10 stories. It's a compressible column of air that's being compressed. So the energy efficient to pump that air around the building, water's not compressible. So you have this 3/4 inch pipe, you can pump that energy all around the building a lot more efficiently. So that's basically the premise of all of this, so you guys understand why it's green. A lot of this stuff started back in the 1980s with chilled ceilings. That's when they first started putting in these radiant panels. What's radiant cooling? I liken it to the sun. You're not heating the air all the way from the sun to here. It's basically an electromagnetic radiation or a temperature differential between two bodies, and that body is gonna flow the hotter body to the lower body. So that's basically the principle of what radiant cooling is. It's the same as radiant heating. People understand that. Like right now I have my fireplace on and it feels great to stand in front of that fire and feel that radiant heat. So it's not dependent upon air movement. So that's kind of the key principle there. So you're just transferring it through that radiant system. So it's super comfortable. Why are radiant systems good? Well, first of all, we always forget this in HVAC because we're always talking about money and putting in the cheapest thing, but radiant is the most comfortable, and the thermal comfort is the reason why we're putting them in there, but it is the most comfortable system out there. It's very simple. You're just putting in a on-off control valve and you're turning the water on and off. With a radiant panel, it sits in the ceiling. You don't really need a lot of space. You don't need ductwork and things like that. Architects love radiant because you could basically put it into any metal panel. No noise, no maintenance, low maintenance, and deals directly with the solar load. And it's actually a requirement for Act 355, we always forget about this, to deal with that radiant temperature asymmetry. Basically what that is that if you're sitting in front of a cold window, you're going to feel cold because of that actually works as a radiant panel. So if you have a radiant panel, it's dealing directly with that, it heats the bodies in the room as well as the people. So it'll be heating up the windows, the chairs, the desk, and things like that. So it deals directly with that if you have a really cold body, it's going to heat that up and vice versa. So that's basically what radiant does. How does it work? Well, you pump water through pipes that are in these metal panels. It's pretty simple. And then about half of it is radiant and half of it is convective. So you have to use a warmer chilled water temperature. I usually talk a lot about it in cooling. Also, these are low mass devices. A lot of people understand radiant in floor and heating. And radiant in floor is a high mass device. So what's the problem with a high mass device is it takes a really long time in order for that to heat up and cool down. So these are low mass panels. So within 3 minutes, if I turn off the water to this panel, it's going to be the same temperature as the room. So what's nice about that, it works great with controls in the building because you can turn on and off that stuff. Whereas especially if you have a problem with condensation or something like that, you turn off and it stops condensing. Whereas if it's in the floor and you're trying to cool in a high mass device, it takes a long time in order to heat up and cool down. So there is the benefit to using that low mass temperature controls with radiant ceilings. So excellent thermal comfort. Very small space, self-regulating, no noise, no maintenance. The only problem, and this is a big problem, is that you're only looking at 25 BTUs a square foot. So with ceiling panel, that's not a lot. I mean, typical places are going to be like 35 BTUs a square foot for cooling, and that's with 100% ceiling coverage. So you're never going to get that. You will supplement chilled ceilings with an air system in order to ensure to cool down those loads in the space, or you can mix them with active chill beams, and that's what we've been doing a lot of, is mixing active chill beams with radiant ceilings in order to get the capacities that need to cover for the building. And we've done a number of designs, and I can talk to you later about that. All right. Then in the 1990s, they said, well, that's great. We really like this whole chilled ceilings thing, but but we need more capacity because that 25 BTUs is not going to cover it. So they came out with this passive chilled beam, and a passive chilled beam basically is a coil suspended in the ceiling. It's cooling only, so you're running cold water through a coil, and basically it works on the buoyancy of air. So hot air rises, it comes in contact with that cold coil, and then it drops into the space. And this is great. You're getting a lot more capacity out of it. The only issue is you can't do heating with it. And it's also pretty dependent upon airflows, and it takes obviously a lot of space in the ceiling in order to get those drafts going. And the key word here is drafts. So you probably wouldn't want to put this over an office space over somebody's head because it's going to dump. And as we know, dumping is not typically very good in an office space. So a lot of times I'll use like a passive beam in a perimeter space, maybe in a really high ceiling or an airport or things like that, where you want to blanket the glass with passive beams. And there is a place for passive beams. I just don't see a lot. We don't use a lot of them. So they like the idea of having more capacity in the early 2000s. We said, but we still need air, because you need air for your fresh air requirement, as well as you need the air in order to dehumidify the space. So that's where active chill beams came in, and it kind of combines the best of both worlds into one unit. And the principle and how it works is that you'll have your primary air coming from your central air handling unit, which comes into the ductwork up here. It comes into this primary air plenum. This is pressurized, usually about a 1/2 inch of static, and the air is going through these nozzles. These nozzles create a high velocity. That high velocity, which is coming out of these nozzles, create a negative space above the coil, and the room air wants to fill that void. So you have that high velocity, negative pressure, and then it's coming out these discharge slots. So if I have 100 CFM coming in from my air handler, I'm inducing 300 to 400 CFM over my coil, which I'm doing all of my heating, sensible heating and cooling with that. And then it's coming out this discharge slot and hugging the ceiling. Due to the Coanda effect, it goes along the ceiling until it hits the wall or another colliding airstream. So with an active chill beams, you're getting very, very good air mixing in the space. So you have the warmer air is coming up, it's coming into the active chill beam, getting cooled down, and then it hits the wall or another colliding airstream and goes into the space. So that's the other benefit. So for 100 CFM, I'm getting 500 CFM of air movement in this space. So it's very, very good for air mixing in that space, as well as comfort. So with an active chill beam, you're getting very high cooling capacity, about 1,000 BTUs per linear foot, which is obviously a lot better than the radiant and other things. So you have integrated cooling, ventilation, and heating, so you can do heating with active chill beams as well. And it uses 70% less air than an all-air system. So the other thing that's great about active chill beams, especially if you're doing an initials design, is that because you're using 70% less air, your ductwork and your air handlers become half the size, or even more. And what that results in is that your actual ceiling becomes a lot shorter. So you can save a lot of money by using less air, by having a smaller duct, and then overall savings in the entire building by having that smaller ductwork in there. Very, very low noise levels, and there's no moving parts, so these things last forever. Like you've seen in New York, the induction units, they basically last forever. So there's no moving parts, no motors, no noise. So that's a lot of the benefits with active chill beams. This is just a report from the DOE, just showing some simple payback with radiant ceilings and chill beams. And basically, they said if they replaced all the buildings in America with these products, this how many quadrillions of energy we could save by using those products. And basically, radiant ceilings and chill beams came in at number one, with a payback of 0 years. And this is for the DOE. The other thing that's really great about active chill beams and radiant is that they pair very nicely with all the other green technologies out there. So a lot of times you're going to be using this with a dedicated outdoor air system. You can see that sort of up there too, with a simple payback of 0. And now with COVID and all the new requirements that are coming out there, this is becoming more and more and more important, and Gil-Bar can tell you all about that. Dedicated outdoor air systems, and in my opinion, that's really the fail-proof way to make your building healthy, is to use 100% outdoor air. The problem with 100% outdoor air is it's very expensive. If you need a lot of it, and again, if you're using that 55 degree and you're using 100% outdoor air, in order to take that air from outside and dehumidify it and then heat or cool it up, you're talking about huge systems. What's nice about this is that we pair great with that. So we can use 100% outdoor air with radiant ceilings and chilled beams, but use a lot less of it. So now your system, like if you have a hospital and you have a patient room, you are exhausting all that air from that one patient room, using 100% outdoor air and exhausting all that air from that one patient room and not mixing it and having no return air and mixing it across the hospital, and taking that air and, I understand, UV lights and filters and all that things, but it totally makes sense to me that 100% outdoor air is going to be cleaner and safer than any of those other systems. So, but again, using these systems and using the coil to do our sensible heating and cooling, we can use also energy recovery wheels. So now I could take that air and the air that I'm exhausting out, I can heat up or cool down the air or dehumidify the air coming in, and even use room neutral air, and then use my chill beams or radiant panels to do my heating and cooling. So all of this kind of works together. And again, when you're designing your buildings and your systems, it really is, and you need to look at it as a complete system. And that's where you're going to save the most money, as well as, all of these benefits that you'll get from that. There's another report, a bunch of reports. Basically, on average, radiant panels and chill beams are going to save you about 30% compared to VAV. So these things also show you, like this ASHRAE journal talks about laboratories, and we could save 50% energy with labs. And again, that's why we're doing a lot of labs. It makes sense. And again, for the same reason, if you have a lab that you're doing 6 air changes and you're trying to heat or cool down people in that lab with 6 air changes, if you're using 55 degree air, you're overcooling all the time. So with active chill beams, basically you can use that room neutral air and just turn on and off the coil to do your heating and cooling and save a ton of energy and money and use a ton less air. So that's really the reason why you can get so much energy savings out of a lab, in that as well as in a hospital and patient rooms. The other reason why people are looking at these is for LEED certification. So obviously optimizing your energy performance is the biggest thing, and we could save you up to 19 points for that, increased ventilation, controllability, and thermal comfort and all that. But again, we've walked the walk with the LEED. We've done our own building. We've done a number of other lots of buildings, so we can help you to get those certifications as well. Maintenance, basically, there's no moving parts, no filter. So basically, all you need to do is there's a screen on an active chill beam you can open up, and you vacuum out the the coil once a year, and that's basically all you need to do for your maintenance on the products. In induction units, you might need it to do a little more because it's down at the floor, and then we can provide things like lint screens to help you to clean them out. The other place where maintenance might be more is like in a hospital because of the sheet changes and things like that, or other environments which might have a lot of dust or other particulates in the air, and you might need to up your maintenance, your cleaning maintenance based upon that. But for the most part, these things are up in the ceiling. You're not getting a ton of movement, and for the most part, you don't need to vacuum out other than maybe once a year. All right, I'm going to go into some design considerations. I'm not going to read all this, but basically, anytime you have a zone with high sensible loads, so basically, we don't do any. You don't want to do any latent loads because otherwise you'll be condensing in the space. That's why we're using that higher temperature water of 56 degrees. So we are above the dew point, and we're not condensing in the space. But you need to make sure that your air is suitable to dehumidify the space. So anytime you have a lot of dehumidification, like in a pool or in a, I don't know, a restaurant or something like that, where you have a lot of humidity in a gymnasium, these systems do not make sense. It includes radiant panels and active chill beams, only because all of your air is going to be used for dehumidification instead of doing just the heating and cooling. So that's basically where these things shine, is where you have these high sensible loads. And anytime you have leaky construction where you have infiltration and humidity coming in, basically it's not good for these systems. These are just some rules of thumb. So the sensible loads. And these are some of the things that we look at basically when we're doing a design, to make sure they're not crazy outside of these kind of areas. So we do have software which can help you to design the products, which is up on our website. But I just wanted to point that out, that, you know, to look at these things closely, to make sure you're kind of in the ballpark. And that, you know, a lot of times what I'll do is I'll look at a plan, I'll look at a room, and then I'll count the seats, and I'll multiply, you know, 200 BTUs of latent load per seat, and that's how much outdoor air requirement I need for the space. So these kind of design rules of thumb just kind of help me when I'm looking at plans, in order to make sure we're not totally out of control. And of course, there's always going to be considerations, and that's why we need to have those discussions. That's all. So this is an active chill beam in the ceiling. That's what it looks like. Just some pictures of them. We have one-way blow, two-way blow. But architects like them. A lot of times we use them in drop-in ceilings. They can be in open space. So there's active chill beams that have Kawanda wings as well. And basically the tiles wouldn't be there. So you need a Kawanda wing in order to get that Kawanda effect and have the throw. So a lot of times architects are getting rid of those drop-in ceilings, and now they're going the open architecture, and you see all the ducts and everything in the ceiling now. So you can get products, including with radiant panels. They'll have they call them clouds, where they'll just hang the radiant panels over people's desks, or they'll have active chill beams with these Kawanda wings in order to create that Kawanda effect that you need in order to get the airflow that you need. That's another one-way throw. Basically, what it's doing is it's drawing up across the window, and then it's blowing the air into the space, so you could have uniform direction. So you have directional flow that you may need with active chill beams. And the slots here, the nozzles are up in here. Basically, the air comes through the coil from the room and then gets blown out the nozzles on this side. If you can see my mouse, I don't know. But basically coming out of these, the slots here, you'll have your air, and the air hugs the ceilings with that Coanda effect. So again, if I'm inducing air, I'm putting in maybe, let's say, 100 CFM from my primary air, which is coming out the nozzles. Then I'm inducing 400 CFM, which is coming over the coil, which is getting heating and cooled. It's getting mixed with that primary air, and then it's coming out the coil, the slot on this side. Schools, we do a lot of schools. A lot of times we will mix active chilled beams with a VAV system, and it makes sense a lot of times because the classrooms aren't used 100% of the times. It also makes sense if you have a large conference room. You don't want to have all that tons of air when you don't need it. So you size an active chilled beam, the amount of air coming in with the amount of humidity that we need to get rid of. So but when those people aren't there, you don't have that latent load, so you can turn it down. So we do a lot of designs with VAV in order to ensure that we're saving the most energy, whether by occupancy sensors or CO2 sensors or humidity sensors. Basically, we can turn down or turn off the air in order to maintain the space and saving energy in that space. So we can help you to design that as well. Again, another look at an active chill beam up against the window. So you may have it blowing into the window and into the space, or it could be just a one-way throw and drawing the air up across the window and into the space that way. We also have they design smaller active chill beams, 1 foot wide. Again, it's architectural stuff. Or we'll have them concealed in the ceilings. And this is nice for New York City because you could take your induction units, which are on the floor, and put them up in the ceiling and gain all that space. So that what happens is that you would be plumbing your air and water from the story above, and then you would take that induction unit, put it in the ceiling, and then you could use that basically as an active chill beam. What's really nice about that is you gain a ton of rentable space, and it's concealed. So a lot of architects like that because you don't see the unit and have those enclosures right in front of the window. You're paying for that view, so you might as well get the entire view. And that's kind of what they would look like, just these slots hidden in the ceiling. So you would have plenum return with the air in that space. And also you could have a continuous look. So you might have a slot LVD grill. Part of that grill will be used for supply air, and where the unit is, you'd have return air coming out of the unit there. And again, architects like that sleek look of continuous look, so we can work with you guys to do any kind of things like that. Or you might have multiple vane units where you could have air coming in on one side and then blowing out the other side. And the units are just mounted on top of those grills in this way. I get a lot of questions on it. That's why I have a lot of pictures on this, because people get confused. The other thing, too, that's nice about these is they do have a drain pan. They're usually not plumbed. So if you have a problem with condensation, it'll collect in that pan, but it's usually not a lot. So we don't. It's just for safety reasons that they put the drain pan there. But that is a nice option that you can have as well. And again, just another look at the grills. This is a horizontal unit, so it can be discharged horizontally into the space. So you'll have the return air coming in here, and then your supply would be coming out of the ductworks on top. Bulkhead or other reasons to use those types of units. It's just different configurations and airflows and how they are blown into the space. So it depends upon architectural needs and things like that. Different grills. I think that one's pretty ugly, but you know. And then, of course, perimeter induction units is a lot of what we do in New York City is doing replacement induction units. taking the old unit out and putting a new induction unit in, with a heftier coil, and with better induction ratios and quieter and things like that. You can save a lot of energy by replacing the old induction units, as well as putting in new custom enclosures over those units. And I'm sure you guys are familiar with perimeter induction units. You know, we do a ton of replacement work with induction units in New York City. And that's an easy, almost simple energy savings. You take the old induction unit out, you put the new induction unit in, you can use your old enclosures, and you can get upwards of a 20% energy savings just right off the bat. It's just a really easy, simple fix in order if you need to get some energy credits or what to be more energy efficient, to be quieter. This is a great way to do it. It works on the same principle as an active chill beam, where you have the primary air coming into those nozzles, creating that high velocity. It comes over the coil, and then it discharges up into the vent on top. So the biggest thing is that we can drop the static pressure to almost an inch of static. These units can use an inch less static and save up to 50% more of energy in a building. They're a lot quieter, and you can imagine if you're dropping an inch of static in your whole entire building, how much energy that can save you. So we've saved a couple of buildings upwards of $1 million a year in energy just by replacing their induction units, which is quite impressive. The other thing is that again, we have the bigger coil, and we're running that warmer chilled water temperature, 56 to 58 degrees. In the older induction units, they would drive very, very cold water and condense. We don't recommend to do that anymore. We recommend to use that warmer chilled water. When you have a wet coil, then you have water, and even if you're draining, you have standing water, and also because your coil is wet, everything sticks to it. So that's why a lot of times those old induction units are totally clogged up, because you had a wet coil in there, and then all the dust collects in there and it'll get cleaned out over time. So that just leads to a lot of things. So with the newer induction units, we use warmer chilled water, so we're not condensing. I know that some companies like to use the colder waters, but we typically do not recommend that. We recommend not to use that all the time, only because of that reason. So we have lower noise levels, and that's also a big concern with some of the induction units in New York. So that's another reason why they want to replace them. So I'm going to go through a case study in Chicago. This is 250 South Wacker. We did a couple of tours at ASHRAE when we were in Chicago of this building. Actually, I forget what engineer's office is in there. I just went to go see them not too long ago. But basically, I was like, oh, we did this building, so they're interested in that. The thing about this building, and really it's a case study on the facade, they basically they put in new glass here, and you're going to see 100% glazing with that E-glass really made a difference with the loads that were in that building. And they were evaluating VAV versus active chill beam. They were looking for LEED certification. And here's basically the existing induction unit system. And I bring this up because it's pertinent to you guys in New York, and just seeing what a difference. And really, this case study really shows what spending your money on the glass does. Basically, we went from 262 tons with the existing building to 156 tons. That's with the new glass. So really, that's the big story in this case study, is that we were able to, they were, I wouldn't say we, I always say we, but they were able to reduce that just by replacing that glass and that facade on that building. So it does make a huge difference. So the existing induction unit system used about 25,000 CFM. If they wanted to go with the VAV system, even with this 156 tons, they would need 86,000 CFM for that 156 tons at 55-degree air. Basically, that 86,000 CFM is not going to fit into the old ductwork because the old ductwork is 25,000. So with our system, we're able to use even less CFM, obviously. So we were able to use the existing ductwork. They wouldn't have to change out all the ductwork for the VAV system because we used less CFM, and we were able to save them a ton of energy by going with an active chilled beam system as opposed to a VAV system, which would be even more than the old induction unit system. So, the other thing is you'd have to replace all the ductwork. So obviously, it was a no-brainer to go with active chilled beams in this case study. And I'm sure it'd be very similar with almost all the buildings in New York. If we were able to do something like this and be able to get better glass and things like that in there. So just showing you how that's done. So they used one-way blow active chilled beams. They didn't want to have the induction units on the floor. They just bought this really expensive new glass. So they took the induction units and they put active chilled beams in the ceiling and saved a ton of energy that way as well. There's another one in California. It is the largest net zero building in the country. And LEED Platinum, they used active chill beams in here with a DOAS unit. What's interesting is they use this night sky cooling system, and maybe you guys have heard of that. Basically, they turn on the heat pump at night, and they're storing the water in the basement for heating and cooling. So they have this 100% outdoor air system. The other thing that's really interesting about this is they use operable windows. So that's why I bring up this case study, because people say, well, I can't use operable windows with active chill beams. Well, you can. Granted, you need to have a pretty good control system, and you need to know what your outdoor air is. And also, this is in California, so they do have nice weather to work with. So I don't know if we'd be doing something like this necessarily in New York, but it's an interesting case study nonetheless. I don't know if we would do operable windows, but the rest of the system would work. So they have an economizer. So it's basically using it at nighttime. So they're able to bring this down 90% savings with this cooling tower on the roof that runs at night and then storing that energy in those storage. I don't know what the storage was, but some kind of tanks in the basement. And then they had a control system to use operable windows. So it would be a little widget that was on their desktop that told them it was a good time to open the window. When they opened the window, it turned off the air from the DOAS unit, and basically you would be able to do your use the window instead of we turn the chilled water off and the whole system off, basically. Chilled water system designs. The other thing that you can do, which is really interesting, is to use a cheap, I say cheap, I shouldn't say that, a DX unit on the roof to do your air handling needs, and then maybe have a dedicated chiller for your active chill beams. Two chillers, one for your air handling unit, which is making that really cold water to do your dehumidification, and one chiller to do your 56-degree water. That's we've done it a lot of times to save a lot of energy that way, only because the warmer the water coming back to your chiller, I'm sure you guys know, increases your COP, and I'm sure Gil-Bar can talk to you guys a lot about that as well. But basically, using a dedicated chiller for that warmer chilled water temperature really increases it, as well as using a dedicated boiler for your cooler water temperatures you're using in heating with an active chill beams. I don't know if I mentioned that, but typically we use cooler water temperatures. You don't want to use 150 degree or 160 degree water in an active chill beam. You can use 110 degree water, and that works really well with condensing boilers as well as heat pumps and other things like that. Ground source heat pumps, we've done net zero building designs with them as well. So there's a lot of application. I can't cover it all, but please, if you're interested, contact me or Gil-Bar, and we can get somebody to help you out with whatever design work you have. And again, having the starting up front is really where you're going to be able to save a lot of energy by looking at the building in the complete system right from the beginning. This is a mixing system where you would have your mixing valve in order to mix that. We don't do that a lot. Typically, you'll have something like this where you have a heat exchanger. So you'll have your 45-degree loop here on your air handler side. So you're using that 45-degree loop, which is going to your DOS unit or your air handler to do your dehumidification. Then we run it through a heat exchanger and we bring it up to 58 degrees for our chill beams or radiant loop on this side. So that's typically the way we do it. I was just discussing something like this at a scout camp, and they have access to a lake. So I was like, man, just throw your coil in the lake and you could just use a ground source heat pump to generate, do your heating and cooling, and then use active chill beams to do that. So if you have access to that, of course, New York doesn't really have access to these things, so I won't cover them. And again, I talked about a dedicated chiller. So the warmer the water coming back to the chiller, the better the coefficient of performance that you'll get. So again, it may make sense to have a dedicated chiller. And of course, we'd love to sell more chillers, so that's always a good thing too. Or you have this running from a cooling tower or a geothermal loop, and even better if I can turn off my chiller and just run my cooling tower to get that 58-degree water, all the better. And a lot of times you can do that just by using that. I can generate this warmer temperature water, turn off my chiller, and save you a ton of energy that way. So it's all, again, it's not design, it's also how it's being used in the system, and being able to turn off or turn down your air and your water at night is going to save you tons of energy in your building. So always think about those things. Typical returns might be a reverse return. These are really simple devices. All you need is an on-off control valve linked to a thermostat, a call for heat or call for cooling, and you could turn on or off that valve. We also do get involved with using 6-way valves, doing a changeover system to go from heating and cooling. So if you have both your cooling and heating lines going down to a 2-pipe system, you have one control valve that you can do heating and cooling and do a changeover. And that might make sense a lot of times in New York, because you'll have different facades of the building where you may have heating in one side and cooling in another. So you might want to go with a 6-way valve and do a changeover system. But typically your whole building will change over at one time, and you'll just do heating and cooling through a 2-pipe system. We can do a 4-pipe system as well. So you can have 4 pipes coming into the active chill beams. Part of the coil is used for heating, part of it is used for cooling. The problem with that is obviously you have less surface area you're using for both heating and cooling, so it's not as efficient, but sometimes you need to use a 4-pipe system if you have different water types. So if you have glycol in your cold water, and you don't in your boiler water, or your boiler, you don't want to mix your dirty boiler water into your chiller water, then you probably want to go with a 4-pipe system instead of a 2-pipe changeover system. And that's about it. I'm going to open it up for discussion at this point. I'm right on time.
All right, I appreciate that. We do have one question, but if anyone wants to ask any questions, do it through the Q&A. If you think of anything afterwards, just email us at theacademy@gilbar.com, and we'll get those questions answered for you. John Carl, there's one question that came up in the beginning. Is how do you maintain RH in an operating room with chilled beams? Do you need a separate supplier for humidification?
Yeah, so you're going to have your dedicated outdoor air system, which is going to do all of your humidity control with that. So you size the amount of primary air to basically get rid of the humidity in the space. So a lot of times they will use VAV controls, or you just might have a constant volume control based upon the space. But typically it's again, that's all the humidity control is done through your air handler. You don't do any humidity control with an active chilled beam or radiant system.
Great, thank you. We'll just give it 20-30 seconds, see if any more questions pop up, and then we'll call it an end, and we'll see you next time.
All right. Well, I just want to, again, I appreciate what you guys are doing, and I look forward to more training sessions like this. Gil-Bar does an excellent job. They're an incredible partner for us, and worked with them for many, many years. Very experienced and dedicated staff. I love doing these things. I prefer to do them face to face, and I prefer to do actual project-based things. We can go over your designs. We have incredible engineers, and so does Gil-Bar on hand that can help you with these designs and kind of link you with the products which may or may not make sense for you. Obviously active chilled beams and radiance is not going to be the end-all be-all for every project, and Gil-Bar has a number of product lines and a number of things that they can help you with on those product designs. But getting us in first, getting us there in order to get an eye on it, maybe we can offer some suggestions that'll help you with those projects.
Thank you. We'll just give it another half a minute and see if anything else pops up.
Obviously, I could just keep talking for hours and hours, but I want to be.
You're like another Gabinelli.
Yeah. It's kind of hard with these though, because you don't get any response, or I'm talk with my hands and stuff like that, and I don't know. It's hard with the crowd participation always makes me a little bit more interested. A lot of times talking to a computer screen isn't that much fun, or even listening on the other end when there's no participation. I don't know what people are interested in, and that's why I always I like to have more of a live discussion.
Of course, understandable. All right, I guess there's no more other questions, so we'll just close it out from here. Appreciate all the work. Thank you, everyone, for joining us.
Thank you.
Thank you. Good day.
Bye.